Welcome, everybody. I'm happy to welcome you to session number 9 of the EMP-E conference. It's the session Data and Model Transparency, quite essential for all different topics, I would say, in this area. So I'm happy to that I can announce 5 different presentations to you today. And before we start with the first presentation, a few organizational information. So this session will be 1.5 hours. We will try to end a bit earlier because I was told that the next session is exactly 3:30. So we will try to give you time to switch rooms. And the plan is that each presentation will be 10 minutes, and after that you will have 5-minute time for questions. And you're very welcome to already write questions into the chat during the presentations. And then I will, by order of appearance, I will ask you to pose your questions. If due to any kind of reasons you're not able to unmute your microphone or whatever, you can also write it in the chat so that I can read the questions. But otherwise, it would be nice if you do it yourself, and then also if you then switch on your camera when you ask the question. That would be really good. Okay, so more people joining. That's really nice. So I'm happy to announce that we will start today with Robbie Morrison. And 1 second. So, and his talk, he is already sharing the screen. So his talk will be about open data for energy system modeling, data paradigm, semantics, metadata, system buses, and licensing. Quite a long title. Then afterwards, there will be Carsten Heuer with the presentation on implementing FAIR through distributed data infrastructure. Then Mirko Schäfer, open data-based carbon emission intensity signals for electricity generation in European countries. Then it will be Antonio Frangioni, I hope I pronounced it right, to co-presenting with Sandrine, sorry, I forgot the last name, co-presenting with Sandrine Charousset. And it will be, the talk will be about Plan4S, SMS++, an open modeling library for evaluating long-term electricity system costs and flexibilities. And then the last one will be Matteo Giacomo Prina. Sorry for not pronouncing it correct. You can correct me later when it's your turn. I will try to learn it. A comparison and cross-validation of energy system models. So looking forward to 5 very interesting talks. And so that we do not lose time, we directly start now with Robbie. The floor is yours.
Hello, everybody. I've started putting this in my talks. I'm actually, it's an apology to the younger generation, and I went down to the first Fridays for Future school strike and wrote them up for Wiki Tribune. I interviewed their leader, who happened to be Luisa Neubauer, and what was remarkable was how young the students were. So my apologies. For some context, I started a high-resolution modeling of national energy systems in 1995, and I added a GNU GPL v2 license to the Decode code base in 2003 and tried to build a community. That's probably the first open energy system modeling effort. I'm fortunate to be able to volunteer part-time for the Open Energy Modeling Initiative. I don't have an institutional affiliation. I'm not going to cover some of the detailed licensing material I gave in the skills workshop on day 1. So the context. The data we're talking about is non-personal, so that takes the privacy issues off the table. And it has been or can be made public legitimately, which takes the commercial confidentiality issues off the table too. We know this openness is driven equally by transparency, but also opportunity. And I argue this journey is going to be long and arduous. Open data trails behind open modeling by quite some margin and requires substantially higher levels of cooperation. I also argue somewhat provocatively that data should be seen as a social construct. Here's a touchstone definition from the Open Data Directive from the European Union. And open data as a concept is generally understood to denote data in an open format that can be freely used, reused and shared by anyone for any purpose. So that's actually quite a encompassing and satisfactory definition to work from. The motivation is that, as I sort of indicated earlier, project teams can work on their code and their problems and their scenarios, but data is something that is applicable across the wider community, and that's why we need to deal with it as a community issue. I'm very happy that some of the themes I put in my slides are already covered by people like Daniel Hookman and Krutz Borges. So I'll skip over and I'll just concentrate on the things that I'm going to say that diverge from some of those earlier themes. And I'm going to cover some projects later. I also want to echo the comment by Kirsten Van Mark from PT Yacht that we should not be reinventing wheels in communities, that we should be doing this within our existing world. I'll skip through this, but this is the code data landscape from the perspective of a project, and most of that will be relatively familiar. You know, the source code, and there's various types of data and so forth under various legal constructs. But going up, looking at it from the other end of the telescope, there are a number of interacting themes that have to work together, and the building blocks are starting to come together, but they still need a lot of work to integrate them. And I want to pick out two ideas on this slide. One is the idea of legal metadata. We need to start putting license information into data sets, and also the contributors lists, because of the data, the most common data license we use, which is the Creative Commons by 4.0, requires attribution. And then that's also closely related to provenance tracking, which is also closely related to data suitable version control. And I don't think we're there on any of those themes at the moment, so I'd like to highlight those. Here's a kind of a simplified view of the structure of the system, data flowing mostly from left to right through observations or generated numerically. And we can expose it through the web. We can collect it in data portals under community curation, and they have to be internally coherent as much as possible. And then we need to interface with those. We've heard the concepts of gateways and things earlier in this conference. So I'm going to talk about a data bus, which is a particular project later on. And so that's just a kind of a very intentionally simplified schematic of the system we're looking at. I've looked a little bit at linked open data. Linked open data is a web-based concept that stemmed from Tim Berners-Lee, where you have semantic triples. So you have two entities joined by a relationship. So X marries Y for example, and then you can collect all these things and naturally create dynamic knowledge graphs. Whether this is going to be useful for energy system analysis is unclear to me, but I have a couple of publications down the bottom which are worth reading in that context, and it's something we could discuss, or we should discuss as a community, about whether we want to look more closely at linked open data. Open science has been covered strongly thus far, so I'll skip over this. I'll also mostly skip over this, but the French government released official policy mid this year, and one of the things they were pushing for were canonical data sets, and so that's also a theme that's been running through this conference. Data semantics are vitally important, and they're domain specific, and they're best communicated using formal ontologies that cover naming conventions, definitions, and relationships. And I'll talk about one project later on. But I just say earlier in this event, the JRC representative urged that energy system analysts align with Eurostat practices, and that's something we should look at. Technical standards are also necessary and challenging, but this community is very technical. And the thing I think that is most difficult is data and version control, provenance tracking, and attribution logging. That's a technical area which has not gained sufficient attention, in my view. Sharing of scenarios was discussed, and I'll come across, I've mentioned a project a little later. Now, this is a bit left field, but the European Commission is busy developing a data act, a proposed data act. There's no draft legislation, but the key objective is the improved public interest business to government information flow, and they will probably modify the 2016 Trade Secrets Directive in order to facilitate that, because some of this information will be covered under the idea of commercial confidentiality. It's unclear to me how this B2G information will actually spill out into the community, into the research community, including. And so I just put that as a question. But I would suggest with suitable anonymization, this could provide a valuable source of representative cost information for current technologies and constructions and so forth. I put in a submission on I put in two submissions on the European Union Data Act. And the second one, I argued that statutory support is needed for open data. To my knowledge, there is absolutely no statutory support for open source software and open data anywhere in the world. It entirely relies on licensed texts drafted by civil society. And I argue that the statutory support would be would resolve a lot of issues that are open-ended at the moment under the present regime. Just a note, and this is also a little left field, is that I actually think that open source software and open data naturally spill over to the global south, and that's a nice area of natural technology transfer that we can push as a community. 4 or 5 representative projects just pulled out more or less within my field of view. The Open Power System Data Portal has been going through since 2016. It serves frictionless data packages from the developed by the OKF, the Open Knowledge Foundation. And I noticed that Daniel talked about those packages or a modified form of those in his presentation. Issues remain with licensing. The project draws from the ENSO-E transparency platform, and the legal context is still difficult. The Scenarian DB project from the Rainer Lamona Institute and others is an attempt to collect scenarios, both in terms of their definition and their later processing and interpretation. So that may be an initiative that can be drawn upon. The open energy ontology has been mentioned a couple of times in this event, and it's a vitally important project. It's licensed CC0 1.0, so it's essentially public domain. And it's anchored in computer science, and it parents off a thing called a basic formal ontology. So it's very well structured. So that's something to look out for and to work in to our workflows, data workflows, and so forth. The ERA data metadata project, which is not limited to open data, is also looking at metadata standards informed by fair data principles, and these of course need to be machine actionable. That's the real issue with metadata. The DBpedia database project provides a smart interface or a gateway into cloud databases, and we should draw on some of that work. Sebastian Hellman has participated a little bit in this community through submissions, and this is really an attempt to the internet, or the web if you like, has very little persistence or guarantees on persistence and change, and this is just a way of dealing with that.
Robbie, the time, closure, perfect.
Yeah,
so
okay. Concluding thoughts. EU data policy would help. Legislative support for open data would certainly assist. Public licensing should be CC BY 4.0 or CC0 1.0, and there is much work for the open energy modeling community to do, I would argue. That's it. Thank you.
Thanks a lot. A lot more to do for the open energy modeling community, definitely. Yeah, we have a few minutes for questions. Are there any questions? For those who joined later, you're welcome to write questions in the chat during the presentations already, or now just by raising your hand or writing them in the chat, you can choose. But if there are none, then I have one question. Do you see any, on EU level, do you see any success, any development on the requirements for open science legislation and law and so on, which you mentioned in recent years?
Yeah, I mean, I talked about the proposed Data Act and how it may benefit this community and some of the issues I thought they should traverse. One of the things I covered in the submission was that there is quite a lot of statutory reporting, either from NSOE or from the electricity exchanges, which is really unsatisfactory for analysts, and I promoted those ideas that they should actually fix those problems. I mean, Frauke knows about the OPSD licensing issue as well. Yeah, okay, there's a question about GPL licensing. I didn't want to go about licensing, but software licenses are not suitable for data. That's the short answer.
Okay, great. Thanks for that. Then I do not see any more questions in the chat. So thanks a lot, Robbie. Then I would switch over to the next talk. That is Carsten Heuer-Klick, implementing FAIR through a distributed data infrastructure. Already sharing the screen? Great. Then the floor is yours.
Okay, thank you very much for the introduction, and thank you, Robbie, for your presentation before, which laid a lot of the foundations I can build on. We were talking here about implementing the FAIR principles we've heard about through distributed data infrastructure. It's about, in the end, about the data bus as Robbie already told you. So there's a lot of people involved from the LOT-TRIOS project here. So the challenge we were thinking about, and we heard of this before, is one thing is energy system modeling remains important for policy development, but as we go around, and we heard this before, there's many databases which exist each in its own flavor. So we have different data accesses, different data formats, different data licenses, if they have licenses at all. Sometimes they are hard to find. You only find them if you know where they are. Sometimes you can fairly easily find through Google. So it's pretty weird and pretty different things around. So data collection is a very labor-intensive task, and then you have to start data cleaning, data aggregation. So, and it's repeated by many researchers with different results and over again. And often data quality is not really known, which data you get. So one solution we see here is a metadata catalog to more easily find the data. So the idea is here to have a metadata catalog which harvests the rich metadata. So to come from this discussion this morning here, from the available data sources. So it needs to be more than just the author and the year. And so it really needs a more detailed description about the data. Then you can start using the catalog to discover the data. And the metadata should then contain the actual URI, the URI to the actual data, so that you can find the suitable metadata fact sheet of a suitable data set, and then you can directly go and access the data. And if it's not something like a data file, it would be also very good to have some interface descriptions if you have a database there. So how can I go there and find and download the data or access the different data? Here we mostly use the OEP and the Open Energy Platform metadata string. Currently there is an extension of linked data under its way so that you can use Ontology. So it's about to be released the next couple of days. So the second challenge is, and this was already Robbie has also been talking about, is provenance. So usually from some source data, there's many processing steps from the original source data to the final published results. So in the blue line, we have somebody getting some source data, do some data cleaning and do some data aggregation. This is the same person, the same institution, but also, as we see in the red and the green lines, there may be different persons and maybe even different institutions involved from the source data to data cleaning and data aggregation. And all the different data sets then go to a certain model, and which comes to some result data. And this may be somebody very different tool, different institution, different person. So therefore, it's very important to trace the workflows which have been involved from some source data to the final result. So, and this is where the data bus comes into play. The data bus is a virtual bus. It can address files on the web and coordinate data flows based on data ID metadata. There is no actual data which is uploaded to the bus. It's only the metadata. So we have some decentralized data storage with some research data we're interested in or somebody wants to publish. And then you put the metadata, in this case, rich metadata, to the data bus. And then as a user, I can go to the data bus and query the data bus and search for suitable data sets. And one unique feature also about the data bus, it can also have collections so that I can group data which belongs together. So like something like a scenario which is consistent of different input and output data, I can make a collection that says these data sets belong together. So I can find the data bus collections. And from the data bus, I get the download links to the actual data storage. And from there, I can go and fetch the data and have it available to myself to be able to work with it. So, and what's also important, unique data identifiers are created by the data bus so that you have persistent identifiers to be able to reference the data. I can use these data IDs to reference a data set to the original source data, which has been used to derive this data. And also one unique feature is I can make incremental modifications to this data. So I can say, I've taken this data set, I've cleaned it, or I've aggregated it, and I can re-announce that there's a cleaned and aggregated data set of an original data set. So people can start reusing work, or better start working using some of the work somebody else has done, and we don't have to do this over and over again. And therefore maybe create a more efficient data economy in working with the data. So the complete architecture concepts look like this. If we go from the left to the right, and thanks for Robbie, you made this nice graph for us. We have data on the left-hand side. In the good case, it's already registered with metadata to the data bus, which is on top. You can query the metadata, download it with SparkQL, then maybe you have a data cleaning service, and you announce we have cleaned data, write it to the same or different repository and make it available. And you can also put provenance information aside to it and also register provenance information to the data bus. And then somebody else can query for this data, use this data in a model or service A, and publish some of the results, announce it back to the data bus. There's now results. So the output data and provenance stores don't need to be stored at the same place. They can also have different places like a prof store where I can store the provenance information. And then somebody else can do this over and over again and use the data which has been published and register it for different servers and announce that there is new data available. And this makes it all much more transparent, much more easy to find. Or maybe if I have found an interesting data set and I would like to know where does this come from, so I can go backtracing and find the original source data or some intermediate data, maybe where I want to do a different analysis. So this really should help and make data finding and discovery much more easy and make it all more traceable what we do with the data in the different models. So the third challenge is also here, what is all the data about? So currently each data source comes with its own annotation. So one sample from meteorology, so which is my background, like if you talk about solar radiation, so one common term is used as GHI, so it's global horizontal irradiation. Somebody just write in there global radiation, so this could be the same thing, that it's global radiation, so the total radiation on a horizontal surface. By the way, often also mixed up is radiation irradiance. The one is an energy, the other one is a power. But unfortunately, often the numbers are the same if you go on hourly resolution and a square meter. But also a different term used is surface downward irradiation. So this is something which is used in climate science, because they distinguish between the radiation which is coming from the sun, which is going downward, and the radiation which is coming up back from Earth, back to space. So they use very different terminology. So it's sometimes very hard and difficult to find what you're actually looking for. So taxonomies or ontologies create a data language to annotate the data and make it much more easy to understand what is in the data. And ontologies can describe relations. So like direct radiation is a part of the global radiation reaching the surface. So we can put these things in together. And ontologies make data interpretable also by machines and algorithms. So here we use the open energy ontology, which has also been referenced before many times in this conference. But good ontologies are created on a consensus building and open development process within the community. So this is not done within a few weeks or months. So the development of the open energy ontology is already lasting a couple of years, and it will last a couple more years until we have probably everything in there, and it needs a lot of discussions. Again, I said before, a new JSON LD metadata string can link metadata to an ontology, about to release hopefully in the next couple of days. So
10 minutes are up. So are you coming to an end?
Yeah, I'm almost finished here.
Great.
No, not really, but I will skip over the example. So I will skip. We heard a lot about FAIR. I will probably mostly go through this one example to make it more clear. Is we have somebody searching for some data. We have somebody published some data. We have some metadata in the open energy platform. You announce it to the data bus with the metadata and the link to the data. You can link it to the ontology, and then you can search based on the terms on the ontology with the query, and this will give you the link of the actual data you have been searching for. Another example I will skip now for time reasons is linking of models. So you can maybe use a good metadata description and based on an ontology or harmonized wordings to create data interfaces between different models so that they're better and more easy to convert between the different data sets. We also had an example here. So I will come to the conclusion. The database offers a service to manage and search registered metadata. It gives persistent identifiers for tracing data processing. It can improve the data economy. I've talked about this before. You can better build on previous work, improve the data instead of repeating work of others. It supports implementation of the FAIR principles in our domain. It enables with Ontology semantic searches, which is much better than the bare searching. And of course, it can improve open data exchange, model coupling, tracing of workflows, and collaboration for better scientific results. And if you're interested, there's a number of further resources there on the right-hand side. You can look and use to dive deeper into what we are preparing here. So therefore, I'm finished.
Great, thanks a lot. I'm really sorry, but it's my job to keep us with the time. It's all very interesting, but since we want to hear all 5 presentations and to have time for questions. And there's already the first one from Daniel Hubmann. Do you want to post the question yourself? Or we can all... Otherwise, maybe you can also just read it, Carsten. And then...
Yep. So at the moment, it's already almost impossible to convince dataset creators to use common data formats on consistent ontologies or even provide provenance information in any format. What makes you think that it will be any easier to convince dataset creators or database administrators to add rich metadata that are compatible and consistent across a different database host? I think on one part, we're getting increasingly forced to it. And what we do here, at least at DLR in our institution, and there's the Helmholtz metadata collaboration, which also helps. And this, I really try to force people, or we do that. Many of the metadata, and even of the rich metadata, contains a lot of standard information. And as we do write our models and do our models, I try to push people there that metadata writing gets to be part of data writing. So many of the information I can just put hard code, more or less hard code, like institutions, or I can get the running times of when I've been running the model. I can get also from the computer environment. So many of the data I can actually write while I'm writing the actual data. So this is a one-time effort to enhance writing routines in the models. But this is what we're trying to do, to convince people and make it more easy that the metadata is directly produced automatically with the data which is produced. And I think once we're there, this will probably make it more easy to get the published results. And what we also will do within DLR, we are just in the process of setting in an internal data bus, which we maybe then also will use for tracing our modeling efforts, so that we also a year later of the next PhD students comes, that they can more easily look up what somebody else has been done before in a thesis before, and trace down what has been done and can build up on this. So
thanks a lot. Any other questions? I do not see any.
Maybe one short additional comments. I don't think, and this is some interesting also, we actually don't really need to have common data formats, but we have to have common format descriptions or machine common descriptions, and like good detailed metadata string. This will make, so what we also developing in the project is something like a small script which can download the data, read the metadata, and just pull the data which is described there directly into a pandas data frame, so that you can use the metadata description directly to interpret the data.
That sounds great. Then I have a question. Do you have a feeling for how many of the data that is out there connected to somehow connected to energy system modeling has usable metadata? So is it already a common thing for people to put metadata, or I just have the experience with own colleagues who, who do not know what at least metadata is. So do you have a feeling for if it's already in the energy system modeling community a common thing, or are we still in the beginning?
We're still in the beginning. There's a few initiatives like the people who use the Open Energy platform. So if you want to upload your data, you have to create your metadata to the Open Energy platform. Like there's an Helmholtz initiative to better improve metadata production, but we're still a way to go. But something like the databases from the JRC we saw here from earlier, I think was today or was it yesterday, of the different data sets. I think it was today, this morning. I think we can harvest some of their metadata. It's all different formats right now, but if you have metadata at once, it's more easy to convert it to a different version than if you start at zero, and you don't always have to fill in the full metadata set with all the schema description. If you have some good keywords in there, which makes your data findable on the link to the data, this already helps a lot.
Okay, good. Then we have one more raised hand, a question from Patrick Kukartz.
Yes, hello. Thanks for the opportunity. I just want to give a comment on why documentation, or how people would think that people would add documentation to data sets or any other scientific output in the future. I guess it's up to us that we create an environment where the work which is put into the creation of a good data set or a good piece of software is a community effort to give an incentive that data sets or software can be citable and appreciated in the future. So this is basically not part of infrastructure development like the data bus is, but it's more a community task that this work is appreciated, and therefore that someone gets a reward when putting this effort into that. So since we have a good part of the community here, this is just something I wanted to mention.
Thanks for that. So good final comment for this presentation. So I would thank you again very much, Carsten. Then I would hand over to Mirko. Mirko Schäfer will give us a presentation about open data-based carbon emission intensity signals for electricity generation in European country. And then just one more comment, it would be great if you could have the chat open, because then you can see the signal that there's 1 minute left. And otherwise I will say something after 10 minutes. So go ahead, the floor is yours.
Okay, thanks for the introduction, and thanks also to the speakers before me. I'm not going to read this long title again. It's this presentation is rather about one specific and not so big data set, and less about the general data and data processing issues. So I already learned that we probably work a little bit on our metadata and also on the license. So thanks for the previous speakers. The result of the entire thing is more or less what you see on the left side, and that is EU emission factors for electricity generation. And here we are treating only direct emissions from combustion, so only from burning things and power plants. And what we wanted to have are emission factors, that is the amount of CO2 emissions per produced kilowatt hour, per technology, per country for European countries. And based on code you can run yourself, data sets which are available to anyone, so that something where we can give you the entire code and you just run it and you get this. Besides, you don't have to access additional databases for efficiency or the like. What you can do with that is that you can then take just these per country, per technology emission factors and multiply them with generation time series, which then helps you to get an carbon intensity signal per hour. So that is something which, for example, is used for operation, that you somehow want to optimize your system based on the grid emission intensity, or if you afterwards want to analyze what is the emission intensity of power generation in a certain European country over time. And the method I'm going to present you that is straightforwardly possible to be extended. So there's a lot still to do. We are just providing kind of the framework where you can jump in and do more stuff. So the idea behind this is that we wanted to use as less as possible data sources. And so we took on the one hand the EU ETS transaction log. So whereas companies like power plants in Europe have to put in their registered emissions inside of the EU ETS scheme. So there you have kind of the verified emissions per power plant. So we got the emissions per year, per unit. And this we wanted to just compare with the generation per year, per unit. And this is something we took from ENTSO-EE. They are providing per unit generation time series. So you can just sum up from ENTSO-EE the time series, you get the generation per year. You take from the EU ETS log the emission per year, you divide one by the other, and you get the efficiency. The problem with that is that there are different names for the same thing. So you have to match the IDs used in the transaction log with the IDs used by ENTSO-EE, which is quite cumbersome, but which we did, and we provide the complete transaction list. Once you've done that, you can just look at the emission intensities per unit and can do a certain consistency check for different technologies. So we collected all the gas power plants, all the coal, so hard coal, lignite, and then everything which is other fossil. And we checked, okay, if we do that, so emissions per unit divided by the generation per unit, does this give reasonable values? And there were certain outliers where we don't know exactly why, but which obviously are wrong. So we kicked them out. And afterwards, what you keep 554 units in Europe with a total capacity of 205 gigawatts. So that is now our base database of per unit emission factors. Now we combine all these technologies, so all power plants from a certain technology inside a certain country with their generation, and this then yields per country, per technology emission factors. That is what you see here on the left. So we have that now for gas, for hard coal, for lignite, and other fossils for all countries where you find sufficient capacities for these technologies. And this is the input which you, if you want to, you can now just download, multiply it with your generation time series, and get this dynamic grid emission factors telling you the emission intensity in a certain hour from the production in a certain country. But we also wanted to compare that with something. So first what we did is that we just analyzed this a little bit, look, does it anyhow matter, or is the per hour emission intensity in a country more or less always the same? But by plotting it over time, looking at this emission duration curves, we see that depending on the country, the emission per hour for the generation mix is very, very different. So for France, there's a lot of nuclear most of the time, so it's rather flat. But for Germany, it's really depending on the hour, what the emission factor there is. Besides that, what we were missing a lot in the literature is that if you are calculating these kind of emissions factor, either per technology or over entire countries, you somehow want to compare your result with another way to do it, because otherwise you basically you're just going forward and you have to trust what you're doing and the data and the entries are all right, but you have nothing to compare against. So we said, okay, we now have emission factors per technology, per country. Now we need time series of generation per technology and country, combine that, and then get an emission factor per country for 2018 for a given, for a given country. So that is the overall average emission intensity of the generation mix of the given countries, calculated from the bottom up, first using the power plants, their emissions and generation, then using the generation per technology in the individual years. That is what we call the bottom-up methodology, yielding an emission intensity for the power generation per country. And then we looked into literature, and for example, the European Energy Agency, they're also publishing emission intensity from power generation per country, but they are doing it completely differently. They're doing it top-down. So they take from the UNFCCC the published or reported emissions from the entire sector, and they take from Eurostat for the entire year all the energy balances. And based on these data sources, they calculate top-down, based on these reported statistics, the emission intensity generation. So it's a completely different way, and we wanted to compare these two. And on the sideline, in the code which we have published, is also now the entire method from the EEA available, so you can do it yourself now and not only to rely on the given data set from them. If you do that, you see that more or less both methods agree. So by, for example, giving France a low emission intensity due to their nuclear fleet, and on the other hand, for example, Poland or Germany, a higher one due to the use of coal. But depending on the country, you have on the one time, the bottom up is higher, and in another country, the top down is higher. So these are all things which have to do with the data behind that. So for example, if you look at Italy, in Italy, you can see that the reported generation to NCOE is often miscategorizing other fossil for gas. So if we do the bottom up methodology, we put in a lot of other fossil, which has a higher emission factor, whereas the reported statistics correctly use gas. So if you do it top down, you get a lower emission factor. Then the top-down methodology by EA, for example, also uses auto producers and main activity producers, which for other countries also changes a little bit the picture. So doing this bottom-up and top-down both together, you really can find out, okay, what are data reporting issues and what is the influence of using specific methods or data sources for calculating these emission factors. So as I said, that is only a framework, because on every level of what we are doing, there should be done more. The first very thing is just increase the matching. So find more translation from the EU transaction log with the NCOE power plant log. So that is something, as soon as you find one, you can just enter it into the code and then it runs itself. So we are now adding more from the UK, because there, Ayrton Burns did a different project where he did exactly that, and we can just put it in. Then we have to check the data at the plant level, because for some power plants, you get emission factors which are completely off, and we want to understand why. Is it just data issues in NCOE, or are the emission factors really high because how they are operating the plant? And the last thing, and that's actually much harder than most people probably know, is consolidate the generation time series. So NCOE is giving you all these time series per hour, but there are a lot of misallocations, miscategorizations, or missing data. So if you take on the one hand the NCOE per hour generation data for your bottom up, and on the other hand, the reported statistics from Eurostat, for example, you're talking about very different, depending on the country and the technology, very, very different energy values. So you have to somehow put that together to consolidate the generation time series. So that's it from my side. So this work was mostly done by Jan-Frederik Unneberg, who's the lead author also of this paper, and yeah, then also Anke Weidlich and Leonhard Gefühlner. And the preprint is already available, and the entire code and the output data is also online. So you can just download and play with it. And we will work on our metadata and licensing. Thanks.
Thanks a lot for that. Sounds like a really useful tool and a lot of data work. Are there any questions? They are clapping hands. Or is it a question? Benam Zakeri?
It was just clapping.
Okay,
I'm
great.
impressed. Great work.
Great. Okay. Then where can you access the software, asks Ludwig.
Yeah, if you, sorry. So in the archive, you find the preprint, and in the preprint is a link to a GitHub repository where the entire code is online. And we use somehow corrected NCE generation data, which we put on Zenodo. I hope we were allowed to do that. And the end result is already also on Zenodo. So these emission factors and also the emission time series.
Great. Then Johannes Thema.
Yeah, so just to understand correctly, in the end, you did find a way to correct for all these huge deviations that you found and yeah, to solve those data issues?
A bit. So what we didn't want to do here is to go per country, per technology, and do the fixes we think make sense. So we have just kind of one uniform methodology which runs through it. And then what you would have to do now is that you, for example, you know, yeah, thanks, Ludwig. You know that in Italy, this generation, what is reported as other is usually gas, and then you correct that. Then you go to another country and you say, okay, here usually the generation from hard coal is underrepresented in our data by 20%, but you have to do that per country, per technology. So that's why I say that it's a collaborative next step. So if someone knows something about certain technology data in certain countries, you can just put that in. But here in our basic framework, we just worked with what we have. We did some scaling based on the NCU fact sheet, and we'll add some scaling based on comparison with Eurostat, but we didn't look at specific power plant corrections or specific generation technologies in certain country corrections.
Then a question by Carsten Heuer-Klick.
Just a very short remark. So the corrected data set you put on Zenodo is just an example. Like in an improved and enhanced data set, you could link to an original source data set, as I told before. I just thought it was a good example for this.
Yeah, and you don't have to use that. I mean, that's the idea here. You can also, for example, if you say, okay, it was nice what you did with your EU ETS data, but we rather take the emission factors we already have. You just plug them in and run the whole thing with other emission factors per country, per technology. And if you say, okay, we already have better generation data because we worked half a year on correcting and consolidating, then you just exchange the generation data. So it's kind of modular.
Perfect. Thanks for that. Then thank you very much, Mirko. And I hope you will find many people supporting that work and using that work. But I guess so, since it sounds really useful. Then we switch over to the next presentation. And that is Antonio Frangiono and Sandrine Charousset. So you will have a co-presentation. You will present together. And it's planned for SMS++, an open modeling library for evaluating long-term electricity system costs and flexibilities. And please also open the chat so you can see the sign that there's only 1 minute left for the talk, so that you can keep to the time as good as Mirko did. So the floor is yours.
Okay, so thank you very much. I hope you can see the slides. Putting it full screen. Okay, so thank you very much for the introduction. So together with Antonio Frangiono, we're going to explain what we have done in the Plan for Us project with that library, which is an open modeling library. So it's not something to do with data now, but more with open source code. So we'll introduce the model, then the solving library, and if time is left, a few results. So first, this was a joint work that was done in a NATE 2020 project called Plan for Us, whose objective was to implement models and tools for helping to optimize and simulate the European energy system, contributing to the European targets for reduction of emissions. And in this project, we have developed many tools, among which the one we are presenting today, which is called the Plan for EU model. So this model is focused on the electricity system. It's done for simulation and optimization. It also includes multi-energy assets, which bring flexibility to the electricity system. It has a modular geographical perimeter that can be one country, Europe. It can represent sub-countries. It also includes uncertainties about demand, risk profiles, inflows, or any other kinds of uncertainties. And also the time horizon granularity is modular. So in it, we represent different kind of electricity assets, like power plants, storages, including the seasonal hydro storages, renewable generation, but also e-mobility or load management. We have a case study with individual load shifting, for instance, ongoing actually. So what can we do with that model? So we have already used it in a case study in the Plant Rise project to show that it was working. So what we have done is some scenario assessment. So we have taken a scenario from the ongoing open entrance project and ran it only for the electricity part to see if it was technically feasible and to see what was its cost and do some sensitivities. We can also do some impact studies of using flexibilities from different kind of assets. We have also worked on evaluating the impact of having different shares of renewable, and we are aiming to evaluate the impacts of climate change with comparing different climatic situations. So this model, it's composed of well, 3 interconnected layers. It can do a capacity expansion, which is minimizing the expansion cost. The capacity expansion layer is also containing another layer, which is the seasonal valuation storage, which computes well, the strategies for optimizing the seasonal storages. And this last layer uses a unit commitment, which computes optimal operation schedules. And you see that all those models are embedded because the green model is necessary to evaluate the functions in the blue model, and same thing for the blue in the red. And so I will now leave the floor to Antonio, who will explain how this is working. So Antonio, this is yours.
Thank you, Sandrine, and thank you, everyone. So as you saw, what we are doing is trying to solve optimization models that have a very specific and complicated form of structure, in the sense that we have complicated problems inside other complicated problems inside other complicated problems. And let me mention that even solving one unit for the time horizon is a complicated problem in itself. So there would be at least a 4th level to consider there. The only kind of approaches that we know that can possibly take this kind of things, and even then not simply are mostly composition type approaches, but to the best of our understanding, if you are to write and implement this kind of approaches using standard modeling tools, this is going to be complicated in general. So standard modeling tools are not very nicely allowing you to run and organize this kind of models. This is why, among other things, we implemented our own take on the modeling system, which is something that is quite different from modeling systems, as you may have seen previously. It has a bunch of disadvantages, meaning fundamentally being in a complicated language such as C++. But on the other hand, this allowed us to tackle a number of opportunities and a number of features that typically are not shared by other modeling systems. What I wanted to mention here in particular is the fact that The model is oriented in the sense that the system is constructed to be extendable, and in particular, your models, the models that you develop in the systems, are thought to be extended, and you are very welcome to add your own models that can become part of the system. And in particular, we do this in trying to encourage code sharing and reusing for optimization of models. So if you, Sandrine, could you please go the next time? So this organization, so that the code is entirely open source. So a small part of the code is the core system, but this core system is actually embedded, is comprised into a larger project for different kind of optimization models, among which, of course, energy. We have specific sub-repositories, which are sort of independent from each other, and these sub-repositories allow you to do your own extensions and implement sophisticated algorithmic strategies that allow you to tackle and solve these larger problems. And also, of course, we have interfaces with existing solvers and also with solvers that we have been implementing inside the system. And I mean, this is already the system is structured in such a way that you can step in and do your own contribution. And if you can go to the next slide, please, Sandrine. So basically what happens then is that, as you have seen, this is the optimizer view of what a system like that looks like. And it's something that is done in terms of, let's say, the shape of the matrix, of the coefficient matrix of your problem. And what happens is that we take these, and please next, and basically really write this in terms of different blocks that are embedded into one another. And my 3 minutes are over. I would just mention one thing that is not in the slide, but I realize it should be. One of the features that the system has is that we use netcdf as the input language and as the input files. And netcdf files are very well structured, allowing you to take part of the model and bring them, to really partition in a very efficient and clean way the data of your problem into the data for the different blocks and put them together hierarchically, which I think it is interesting for this particular audience. Thank you, Sandrine. The floor is yours back.
So thank you, Antonio. So as you see with those nice blocks, so with this, we have implemented fully the plan for you model, and we have tested it. And so the last part of the talk was just to show you that it is real and that we could really run it. So this is an example of a case study that has been done with the techno-friendly scenario from Open Entrance for the year 2030. So we have aggregated some of the countries in order to have not such a big problem. And we have solved the seasonal storage problem using the stochastic dual dynamic programming algorithm, which is implemented within SMS++, which gave us all those nice graphics you see on the right of the screen, which are the different volume trajectories of the seasonal hydro reservoirs in Europe. And on the left, no, that's on the left, and on the right, I think on the left, you can see the marginal costs that are corresponding to all the countries. So the legend is switched because the model is big and also it is stochastic. And here you can see the installed capacity in all the different regions in 2030. And after that, so that was the seasonal storage evaluation. And then once we have computed those strategies for the reservoirs, we can simulate on one chosen scenario over 1 year with a very detailed representation with all the constraints for all the different kind of assets. And so here it's just an example of 3 typical weeks in winter, spring, and summer for 3 countries, which here are France, Germany, and an aggregation of Scandinavian countries. And to show you that we could compute some real schedules for all those assets. And so here it's just a way of representing them with the technologies and with the cost order. And so just to conclude, all this is, of course, available. So you can find the reports and data sets that we have been using on Zenodo in the Plan4S community. And you can find the solvers that are used also in this model, also in GitLab or for Skip on the Skip repository. SMS++ Antonio already said it, and this couldn't have been done with also the contribution of the HP, who developed a nice environment which allowed us to run the model not only on Antonio's Mac computer, but also on our EDF huge cluster and on an Amazon cluster, taking advantage of all the parallelization, and this without having to do anything except running the software. So thank you very much, and we are open to questions, or you can send us emails.
Thank you very much for your presentation, and great that you did it even with 2 persons in 10 minutes. So are there any questions?
I'll jump in. You didn't see me waving. I've worked on 3 energy system modeling frameworks written in C++, and I understand why you would choose it. But the community has moved to Python and Java. Java, Python and Julia. So do you think that's an issue? Choice of language is an issue? Is that going to be an impediment?
If I can answer, yes. So this surely partly is an issue. On the other hand, the point here is that if you want to run the kind of nested decomposition algorithms that you need in order to do this kind of things in parallel, I mean, to the best of our understanding, the other techniques basically are not really able to do that. So the focus of the system is perhaps on a slightly different set of users. So those that are developing the core technologies. And I mean, hopefully this can be enlarged. And of course, having a good interface with more friendly languages like Java and Python would be a fantastic thing that we are thinking of. But really, the kind of models that you are solving are of a size that so far cannot be tackled with any other technology that we know of. And therefore, I mean, first, primus vivere, they say it in Latin, first you have to survive the ordeal of having to solve this kind of guys, and then you surely have to consider making it more available to as many users as possible. But I mean, we had to get there first.
And if I can just complete, for the user, it's completely transparent, and all the workflow is implemented in Python, and it's the software is linked with the open entrance database within Python, and all the visualization scripts are Python. But then we are running the code in C++. I'm not an expert in C++, but it's all user friendly.
So can I just ask which compiler, or is it multi-compiler?
Oh, we have been testing all the recent ones. We have been running on Mac, on Linux, and on Windows. And I mean, I use the C++ is one, and Clang++. There have been a little bit of tweaks to do. We have some of these dirty tricks you have to do tackle. But I mean, it's basically C++ 17, so any modern C++ compiler should do.
Then there's one question in the chat by Oriol Aventos. Is the European transmission grid modeled?
This I can answer. Well, it is modeled, but of course it's simplified, and it depends of the case studies. So the case study that was presented here, we have a European transmission model with one node per region, and region are country or groups of country. And we are currently running another case study where we have disaggregated some countries, and we have around 10 or to 15 nodes per country. So it depends on the data you have. So if you want to model the transmission grid, you need to have some data. So in the other case study, we are relying to the representation that was done in the eHighway 2050 project, where they have defined a more accurate nodal model for the transmission grid.
I just step in for a second. The model itself is very flexible, and you can put in there a representation that is as detailed as you want of the transmission, even AC if you really want it. But of course, then the difficulty of the models scale in a way that you have to be very careful about what you really want to put in if you really want to solve the thing in decent times. But the system would allow you to try to do anything you want, basically.
Great, thank you very much for this very interesting model presentation. We are curious what happens further with it and how it will be used. And then I will hand over to the last presentation of the session today, and it's Matteo Prina about comparison and cross-validation of energy system models. So the floor is yours, and would be great if you can have the chat open so you can see the 1 minute left sign.
Okay, I don't know how to do it. Okay, so good afternoon to everyone. So this is my name is Matteo Giacomo Perina from URAC Research, and this is our work on review work on comparison and cross-validation of energy system models. So the main objective is to identify through a review study the techniques used by researchers to compare energy system frameworks, models, and scenarios. And while several review studies exist on the comparison of energy system models based on their, let's say, theoretical and structural features and characteristics, none of these focus on the comparison techniques of their final results. So some definitions. Framework is an energy system modeling environment to inspect the best future alternatives from a techno-economic perspective. It has a general formulation, so it's not reduced to a single specific case that allows it to be replicable under different assumptions and input data. It is characterized by a certain mathematical formulation and structural boundaries. A model is an energy model is a specific implementation of an energy modeling framework. It is usually characterized by defined input data and assumption, and certain level of resolution and system boundaries. The scenario is the results of an energy system model run. So in this slide, I want to present some initial, let's say, characteristics of these different types of comparison. So the comparison of models, also called intra-model comparison, is characterized by one framework and different models that are compared, of course. Comparison of frameworks or inter-model comparison is characterized by different frameworks that are compared. And comparison of scenarios, where different scenarios obtained by different frameworks are the subject of the comparison analysis. So what about the harmonization in these three techniques? So in comparison of models, the models use the same input data and the same mathematical formulation because it's the one of the framework that is used. In comparison of frameworks, there are the same input data, but different mathematical formulation, while in the comparison of scenarios, we are talking about different input data and different mathematical formulations. So the low, let's say, level of harmonization. The results of the comparison are useful to inspect which aspects for the comparison of models. Usually, the comparison techniques are used to test, to evaluate the impact of resolution. In the comparison of frameworks is used to evaluate the impact of the mathematical formulation and also to identify commonalities and areas of disagreement, while the comparison of scenarios is mainly used, this technique, to identify commonalities between scenarios and areas of disagreements. So the results of the comparison are useful for who? Comparison of model usually for modellers, comparison of frameworks for modellers and policymakers, comparison of scenarios mainly for policymakers. So we have collected different studies comparing models. So we are talking about the first category of comparison, and focusing on the comparison techniques, we have identified all the different indicators that are used within the comparison analysis. And we have identified different categories for these indicators, which are the generation and demand deviation, the cost deviation, the CO2 emission deviation, the computational process indicators, such as the computational time, number of variables, constraints, and so on. And then the simple comparison of some outputs of these models. So for example, generation and demand, cost, installed capacities, curtailment, CO2 emissions. And looking at these reviewed studies, we can see that the most used is the cost deviation. And then we can find the simple comparison of generation demand, cost, capacities, then the generation and demand deviation, and in the end, and also is used the computational process indicators that are used in some studies. Looking more in detail in these indicators, it's possible to find in the cost deviation category some indicators that could be grouped in the same, let's say, cluster, which are the deviation in the objective function value or deviation in cost, where there is the need to define a reference model. So a reference model, it is usually chosen as the model with the highest resolution. But in some cases, it's not possible to select the reference model. So it's also very interesting, this misallocation method introduced by Scheiske and others, which allow to compare different model results without setting a reference case. And also we have seen another interesting indicator is the generation mix error introduced by Poncelet and others. So 2 years ago, we presented at this conference another review studies of the challenges of bottom-up energy system models, and we identified that one of the challenges is resolution and resolution in 4 fields: resolution in time and space, in techno-economic detail, and sector coupling. And we want to keep the same structure here. So we look at the reviewer studies and how they used comparison techniques to evaluate the impact of resolution fields on final results. We can see from the results that the studies focusing on one resolution field are the majority, and the most inspected resolution is the resolution in time. Then there are some of them focusing on 2 resolution fields, and just one on free resolution field, but none focus on all the different resolution fields. And this is important because it is important to decide if a certain resolution field should be prioritized compared to the others in order to maximize the accuracy, and in a trade-off, of course, with the computational time. And then we come to the second category, the comparison of frameworks. In this case, we can see that the studies are, the number of studies is much lower, and also that the years of publications of these works are very recent, with many different preprints. So of course, is a new topic. There are, let's say, the majority of these studies concentrate on the power sector, but there are also some covering all the different sectors. And in this case, we classify the comparison approach into quantitative and quantitative high, where the quantitative is where each results of the considered frameworks is compared to the results through a set of different indicators, and quantitative high if there is this comparison on different set of indicators, but in addition, there is also an evaluation of the deviation through statistical analysis, clustering, and more advanced techniques. And we can see here that just in 2 cases, this quantitative high approach is implemented and are the ones with the higher number of compared frameworks. So the sample, this type of technique require a large sample. Then we look also at the indicators which are used for the comparison, and the most used are the values of the decision variables in terms of install capacity, so the generation sources, balance of solutions, the energy generation mix, CO2 emissions and cost, and less used is the optimization process variable and the hourly profiles. And then in the end, there is the comparison of these scenarios. I think I finished my time, so I will go very quickly. Here we can see that of course, the scenarios that are compared have a higher number, and of course, there is the possibility to use more advanced comparison techniques on the final results. So to conclude, we presented a review of a review study which aimed to identify the techniques used by researchers to compare energy system frameworks, model, and scenarios. The comparison of models, in the comparison of models, we have seen that the most unique indicators are the cost deviation, the generation and demand deviation, and the simple comparison of different outputs of the model, like generation and demand, capacity, and cost. The comparison of models is mostly used to test a certain resolution. The mostly tested is the temporal resolution in literature. And however, no study explores simultaneously the 4 resolution fields that we saw that are important for energy system modeling. The comparison of frameworks, statistical analysis on the deviation of the final results from different frameworks is possible only when the sample of energy system frameworks is large enough. And the comparison is usually based on comparison of the decision variable of energy generation mixes, CO2 emissions cost, less frequently on optimization process variables. And the comparison of scenarios, it can reach higher number of compare results because no harmonization is required. So it's easier to make the comparison, and more possibility of statistical analysis on the deviation of the final results are possible for this type of results. Yeah, and I finished. So thank you for your attention.
Good, thank you very much. Then we have a few minutes left if there are any questions. So far, I do not see any question for here. I take the opportunity to ask one. From you, since you have deeply looked into the comparisons now, do you have any suggestions to make better comparisons? Are there any lessons learned you could share with us?
Yes, I mean, of course, let's say the challenges of this research field of the, let's say, comparison experiments are in, for example, for the comparison of models, for sure, the exploration of all the different resolution fields, so the impact of different resolution in all these fields, in order to understand which one should be prioritized in order to improve the accuracy with the with an eye to the computational time. Regarding, let's say, the others, the comparison of frameworks and scenarios, of course, more studies using, let's say, more advanced statistical analysis on the deviation of the results could be very interesting, which are applied in few studies. So I would say these 2 points.
Great, thank you very much. Also very valuable contribution, since as there are so many models, frameworks, and scenarios around nowadays, the topic of good comparison methods is needs increased attention. So thank you very much. I don't see any more questions.
Can I butt in?
Yeah.
There's a reasonable amount of work aimed at evaluating open source software projects as projects and communities rather than the code that they produce. Do you think that would be a useful route to go down? Things like how much traffic there is on the issues tracker, how quickly things get resolved, those sorts of things. So the social context of modeling rather than the numerical context of modeling.
Okay, thanks for that comment.
No, it's a question to Matteo.
Okay, yeah, sorry. Let me repeat if I understood it well. So you mean, yeah, probably I concentrated in this review a lot on let's say, some aspects of energy system modeling comparison that are mostly quantitative aspects, while you are suggesting that, of course, some other aspects like integration of behavioral economics, for example, in energy system modeling should.
No, I'm suggesting you look at the modeling communities as well, and look at how functional they are to maybe get some clues. Because there will be quite a lot of work in the open source community about on that level, evaluating the communities, the teams, the social context rather than the software itself.
Yeah, okay. Yeah, I mean, this in this work we wanted to concentrate only on the final results, on the let's say, quantitative aspects. But of course, there are so many other aspects to take into account. So yeah, thank you for your suggestion.
Yeah. And then Ludwig Hub has posted in the chat that please check out the collaborative collection of models and frameworks and add or update the ones you know, and has posted the link. So that's also be a signal to everybody. So time is running. Thank you so much for all your very interesting presentations and also the questions. And I'm really impressed and happy how high on the agenda the openness of data and models is nowadays, at least compared to the time when Open Mod initiative and things like that started. So that was really a different yeah, different status at that time. So there's a lot of progress, of course, a lot of more work to do. But we are on a good way, I would say. And yeah, last thing for me to do is now to invite you to the closing session of the conference. I post the link to it in the chat. And yeah, the organizers really ask you to join so that they can receive feedback, which is really important for them. And one topic is also in the session to choose key topics for the next year. So if you have any input there, and anyway, you are very welcome to join, take part, and give your feedback and make suggestions for next year. So thank you very much to all of you, and have a good last session of the conference.